Okay, I think I have already started recording. Okay, good. Okay, again, welcome everybody. This is the day 2 of our intensive workshops. As we announced on the blackboard, today we are supposed to discuss calculations, a lot of calculation, but the calculation is specifically on the Christoffel symbols as well as the Riemann tensors. Okay, so if you are now looking at the questions, it seems overwhelming at the beginning because there are a lot of questions there, but actually some of them are really simple. So I think the heaviest calculation comes from question 2b2, okay, which asks us to compute the Christoffel symbols, and also question 3. Part C. Okay, so I think most of our works today would be these two sub-questions. So again, we are now going to focus on calculation on Christoffel symbol, as well as some calculation on the Riemann tensor. Okay, so yeah, without further ado, let's start from question 1. Okay, so question 1. We consider a space, okay, and this space is just the two-dimensional surface of a cylinder, okay, of radius A, okay. So I hope that you already have the picture about what this looks like, but it should look something like this. Okay, so it's really a cylinder. Okay, but we only look at the surface. Okay, so I think most of you know that we all deal with a metric, and the metric is actually existing on the surface of this cylinder, and the radius is A here. Okay, so this is the line element, maybe from point P1 to P2, something like this. So we are interested in, in general, okay, the distance between P1 and P2, especially when it is a infinitesimal distance, which only means that we are talking about the line element. Okay? But we will come to that later. Okay. So now part A of this question asks, okay, whether this surface is flat or curved. And I have emphasized that I'm asking this question in the sense of intrinsic curvature. Okay. So can any one of you tell me the answer? Or what you think about these questions? Do you think that the surface of the cylinder is flat or curved? Okay, Winky said no. What do you mean by no? You mean it's not flat or not curved? It's just a rectangular plane, no curve. Okay. Okay, anybody has a different answer? Is this? Anybody thinks that it's actually curved? Okay, 1, 2, 3. Wow, okay, nobody said it's curved. So I assume that this implies that all of you agree with Winky that this space is flat, right? It's not curved. Okay, so well, I can say I can put a question mark here. Okay, you all agree it's flat, but let's put a question mark here, whether it's flat or curved. So now let's come to part B. Okay, find the Riemann tensor R, okay, alpha, beta, gamma, delta on this surface. Okay, Winky, as you just answered, it's not curved. Can you quickly tell me what do you think about the question to this part B? What do you think about the value of the Riemann tensor? Or should I not just ask Winky, because it seems that all of you agree that it's flat. So could some of you quickly tell me what should be the real value of the Riemann tensor? Anybody? Before I really do any calculation on this. I know that I've given you the hints in the questions, okay, asking what is the metric on this surface. Okay, but even before we go to that part, okay, if all of you agree that this surface is flat, then what would you say about the Riemann tensor? Can anyone? Okay, Yato said that in flat space-time, R is equal to 0, and I assume you're saying R here, that means the Riemann tensor. Kokhei also said maybe 0. Okay, so let's also write down whether this is 0 or not. Okay, so how to verify this claim? Okay, so now we all want to claim that this Riemann tensor should be 0, but how could we verify this? Okay, the thing is very simple. Okay, as I've given you the hint, right? We should try to consider the metric, right? So to know the metric, we should all start from the line element. Okay, I hope that all of you can see my writing. Okay, I would also like to ask you guys, what is the line element here? Okay, this should not be super difficult for you. Okay, Yato said that it's R square d theta square plus dz square. Okay, very good, very good. You are correct, okay? Except for the R, because I have already denoted A as the radius. So the R should be A. So the correct answer is something like this, right? Right? Because in a cylinder, it would be very convenient for us to use the cylindrical coordinate, theta and z. Okay, to denote the points on the surface, right? And to explain it more concretely, z just represents the height, okay, and theta just represents the horizontal distance here, okay. So you're absolutely right. The line element should read something like this. And this would also imply that the metric, okay, if we call G mu nu, and we want to write in matrix form, and the mu and nu here is equal to either theta or z, okay. I know this is weird because usually we use mu and nu to denote a space-time coordinate, which usually runs from 0 to 3. But in this case, obviously, we only have 2 dimensions. So mu nu here just denotes theta or z. Okay. So if we write down the metric in terms of a matrix, then can anybody quickly tell me what I should write in this metric or matrix? Anybody? If I assume, okay, if I assume that this column is theta, this column is z, and then the first row here is theta, and the second row is z. Okay. And Yato said that it should be a squared 0. I assume this is the first row. Okay, a squared 0, and then 0, 1. Okay, yeah, very good. This is the correct answer. Okay, obviously, this slot here represent the g theta theta component, right? Because this is theta, so this is g theta theta. And g theta theta is obviously a square here. Okay, so we fill in a square here in this slot. And for this one, we have g z z components metric. And because this is 1 here, right? So we have 1 here. And because there is no cross term in the line element, so obviously the g theta z and g z theta components are all 0 here. Okay. Okay, so now we got the metric. Okay, as required by the hints of the questions. So what can we say about the Riemann tensor now? Can anybody quickly tell us what we can deduce from this metric about the Riemann tensor? Because now, don't forget that now our ultimate goal is to calculate the Riemann tensor here, right? We want to verify that the Riemann tensor here is 0, okay? Because now we claim that the surface here is flat. So what can we say about the Riemann tensor just from this metric? Anybody quickly tell us? Anybody? Okay, as I mentioned, now we want to verify these things, right? So every time when we want to calculate the Riemann tensor, of course, there are a lot of ways to do this, but the most straightforward way to do this is what? What is the term that we can use directly to compute the Riemann tensor? Okay. I'm now trying to let you guys think or try to recall what you have learned about the Riemann tensor. Do you recall any formula that directly give the Riemann tensors? Okay, Yato said the Christoffel symbols. Yes, exactly. If you really remember, we have something like Christoffel symbol. Okay, it's a derivative minus a Christoffel symbol, also derivative, and then plus some Christoffel symbol product minus some Christoffel symbol product, right? Okay, now Vincent said that since all elements are constants, then all Christoffel symbols are zeros. Okay, I assume that you're talking about, I mean, for the elements that you're talking about, you're referring to the metric. Exactly, okay. Because now we rely on the Christoffel symbol to calculate the Riemann tensor, which means that we also want to calculate the Christoffel symbol here. But what is the Christoffel symbols? What is the most straightforward way to calculate the Christoffel symbol? Again, there's another formula, right? Can somebody quickly remind us what is the formula? Or what is the form of the formula? Okay, Yato. Okay, very good. Yato mentioned that it's something like a half G. Okay, something something with upper indices. Very good. And then something like this. Very good. Very good. Exactly. Exactly. So now we can see that the Christoffel symbol is in terms of metric tensor, and exactly like what Vincent has just told us, that because all the elements, okay, of the metric tensor is constants, so actually all of these things here should be zero, right? Because don't forget that this is actually derivative of the metric components, and the components now are constants, so they are all zero. So this means that the Christoffel symbol is zero. Okay? And the Christoffel symbol equal to zero implies that the Riemann tensor is also zero, okay, due to this first formula here. Okay, so now if we look at part C, okay, this question is actually designed to let you really verify whether your conclusion for part A is correct. Okay, is that so now because we have calculated the Riemann tensor, which is zero, okay, so we should be able to say that because Riemann tensor is zero, so the spray is flat. Okay, so for part C, actually all of you have done a very good job. We can now verify that the surface is indeed flat. Okay. Okay, so in case some of you may wonder why the cylinder is flat instead of curved, because obviously it looks curved, right? It looks because it's a circle. Okay, if we go back to this picture, because this is a circle here. Okay, we have a lot of circle here, and circle is obviously not flat, right? It should be curved, right? It's a curved line. Okay? So why is it flat? Okay, in case you don't understand this, let's go back to the hint here that the question mentioned. We are now talking about this curvature from the point of view of the intrinsic curvature. Okay, so what this means is we assume that we are just a creature, okay, embedded or not embedded, but which exists only in the space, in a two-dimensional curved space, or the space. Okay, so we cannot observe the whole space here from a higher dimension. Okay, so now we think that it looks curved because we are looking at it from a three-dimensional space. Right. So we are now seeing this cylinder embedded, okay, or this two-dimensional space embedded in a three-dimensional space. So it looks curved to us, but such curvature is not called the intrinsic curvature. Okay, we rather call this extrinsic curvature. Okay? If we are just a small creature here on the surface, then there's no way for us to take the three-dimensional space, which is a high dimensional space, okay, as a reference to look at this space. So that's why we can only detect, or I should say detect or sense or feel, or whatever you call it, the curvature of the space. And actually, Winke mentioned that this space, if we just flatten it out, is nothing but just a rectangular sheet of paper. So to a creature existing in such a space, it would be nothing but just like a piece of paper, a flat paper. So that's the meaning of the intrinsic curvature. So yes, all of you are correct. This is flat. Okay, then let's move on to the second questions. Okay, the second question now asks about a different space. Okay, so it's a flat three-dimensional space. Okay, which means it's just the usual Euclidean three-dimensional space. Okay. I know that this question is a bit similar to what you have discussed yesterday, but I think this is really a good exercise. So I think it is not a bad idea for us to to do some of the revision here. Okay, tackling this kind of flat three-dimensional space. Okay, so let's look at the first part of these questions. Okay, A1. Okay, write down the line element and hence the metric in such a space, okay, in Cartesian coordinates x, y, z. Okay, so anybody can quickly tell me how to write down the line element as well as the metric? Okay, Yato said it should be something like this. If I translate your typing into handwriting, it should be something like this. Yes, very good. Okay, I think this should be the simplest question in our workshop today. Okay, yeah, it's just a good old line element. Okay, we are most familiar with. Okay, what about the metric? What about if I want to write down the metric as a matrix? G equal to, what do you mean, Yato? You mean L or 1 or? Identity matrix. Yes, very good. It's nothing but this matrix here, right? Okay, very good. Let's go to A2. So A2 asks to compute the Christoffel symbols for such space with the use of the Cartesian coordinates. So what is the Christoffel symbols here? Can anybody quickly tell me again? Zero. Okay, why? Yeah, just the same as previous question, right? Because obviously the metric is, is constants, right? Well, actually we can even say that this is nothing but the Kronecker delta. Okay, it's a constant. So because the metric is constants, we have the Christoffel symbol being 0. Okay. So A3. So what about the Riemann tensor? Yeah, also 0. Very good. Also 0. Okay, good. Very good. Now let's go to part B of the question. Okay. Write down the line element and hence the metric in the same space, but in the usual spherical coordinates, okay, r, theta, phi. And also write down the inverse metric. Okay, can anybody quickly tell us what is the line element when we use this kind of spherical coordinates. By the way, Winky said that, okay, coordinate basis does not change at different points in Cartesian. Yes, very good, very good. Yeah, so if we imagine the whole space as having, infinitely many points, and then on all the points, we all have a basis vector systems, right? And because such bases don't change, okay, from point to point, okay, they stay the same. So there should be no Christoffel symbol if we use this kind of coordinate system. Yeah, very good. So Winky has the correct picture, the physical picture of what the mathematical symbols really means here. Okay, what it means by saying that the Christoffel symbol is 0. But what about part B? Okay, now we have come to part B, which asks about the spherical coordinates, right? So what about that? Can anyone quickly tell me what is the line element if we change the coordinate system to the spherical one? Or actually, you guys can just speak up. Okay, you unmute yourself and speak up. I think that would be faster than typing in chat. So now we have come to B1, and we want to know the line element. Okay, to give you some hints, now we're talking about the spherical coordinate. Okay. And then we have some kind of cube here. Well, actually, I'm quite sure that all of you know this stuff. As a revision, I think I can also just do this properly like this. Okay, please excuse my poor drawing. Let me do something like this. Okay. Something like this. So this vector here is r, this coordinate is r. And the cube here is just the infinitesimal cube, the infinitesimal volume. Okay. So what is the infinitesimal length here? Can anybody quickly tell me about this? Actually, I still don't think my drawing is good. Okay, Man Yin has some typing here. You mentioned dr square. Okay, good. Dr square is the answer. I mean, the first part of the answer. And then r d theta square. And also our sine theta d phi. Yeah, very good. This is exactly what I expected from you guys at the very beginning. Okay, or to recap, this length here is exactly dr. Okay, this here is r d theta, and the kind of horizontal length here is nothing but r sine theta d phi. Okay, so by Pythagoras theorems, the square of the line elements, it should be something like this. Okay. So what would be the metric? Can somebody tell me quickly? What is the metric? I would like to say that Kwok Hei also has given a correct answer on this. Vincent has typed the XYZ, which I think is correct. But because this is just, what you just mentioned here is the coordinate transformation between the spherical coordinates and the Cartesian coordinates. And now we are not even talking about the Cartesian coordinates. Yeah. So, so the line element should be something like this. Okay. So what about the metric? Can anybody quickly tell me? If I assume that this is GRR, this is G theta theta, this is G phi phi, then what is it? What is the actual value? Okay, Yato and Liv and Winky have given the correct answer. Yes, very good. It should be R1 here for GRR, R square for G theta theta, and R square sine square theta, okay, for G phi phi. Okay. In case if some of you don't know what's happening here, we're actually just substituting the result here into the metric. Okay, here and here. Okay, because the metric is supposed to be written as GRR dr square plus G theta theta d theta square plus G phi phi d phi square, right? Yeah, because this is exactly the definition of the metric, right? Is the coefficient in front of the all of the line element here. Okay, and of course there should be there's supposed to be some cross term here like r phi, dr d phi or something like that. But because in our special case, in this specific example, we have all this cross term being 0. Okay, so this is the correct answer for the metric. What about the inverse metric? Okay, the question doesn't only just ask about the metric. What about the inverse metric as well? It should be something that can be written like this. What is the inverse metric? Well, actually, for better looking of the note, I think I should open a new page. Okay, so now we have the metric looking something like this, something like this. Then what about the inverse metric? Can anybody quickly remind us about this? Okay, Yato and Liv have mentioned something like this. Okay, 1 here, and then 1 over r square, and then 1 over r square sine square theta. Okay, very good. Very good. This is exact answer for the inverse metric. In case you don't know why this is the case, it's because when we multiply the matrix with its inverse, we would only get the identity matrix. Okay, so it should be quite straightforward to show that when we multiply these two matrices together, we will get the identity matrix. Okay, very good. So now let's come to part B2 here. Okay, actually part B2 is where the real fun comes in. Okay, so now we are asked to compute the Christoffel symbols directly, okay, with the use of the spherical coordinates. And actually this is the main part of our workshop today, okay, because we are supposed to do a lot of calculation of Christoffel symbols and also Riemann tensor, which is next question. Okay, but first we have to know the Christoffel symbols, right, in order to get the Riemann tensor. So now we focus on these Christoffel symbols. Okay, so if you were asked this question, what would you do? What would you do? Well, actually, I have asked this question before today. Can anybody quickly remind ourselves again? If you are asked to compute the Christoffel symbol, what will you do? This is the most straightforward way to do this. Yeah, Yato said that already in terms of the metric elements. Yes, very good. If you remember, we have written something similar, right? This formula, okay, in terms of the metric. Okay. So this is a very useful formula. But now, obviously, the metric is not just constants, as what we did before. So we have to be more careful now to calculate this Christoffel symbol. So we have to be really careful on indices. So let's recall what the formula really looks like exactly. So actually, I have my own way to memorize this. I don't know if you guys have memorized this or not. But actually, I have a good way to memorize this. So just a little sharing how I memorize this. I would just look at the first index here is alpha. Okay. Then the first index should also be alpha. And then I have two indices here, as well as a contracting indices here. Okay, so now I have three indices to play around: beta, gamma, and delta. And obviously, beta and gamma here, okay, coming from here, kind of share the same mathematical purpose, or kind of the same mathematical positions, right? Because they come from the Christoffel symbol directly. Okay, so they can be grouped as something similar here. But delta here is obviously quite different from beta and gamma, right? Because it's a contracting index here. Okay, so if you ask me, okay, beta, gamma, and delta here, which is special? Okay, then I would rather say that delta here is special. Okay, because it has different, you can say origin, okay, as these two indices here. So now we have three terms here, okay? And obviously, this term is special, right? Because it has a minus sign, okay? But these two terms here, they all have a plus sign. So my trick of remembering this would be the special index here, delta, would be the derivative here, the derivative of this special term here. Okay, and for beta and gamma, it would be these two index of these two terms. Okay, so I hope that you understand how I try to remember this. Sorry if I make the writing too messy here, because the point I want to make here is just to kind of visualize how it would be possible to remember this formula. Okay, so now we have this formula, okay, to calculate the Christoffel symbol. But okay, how do we do this exactly? Okay, okay, I have to confess that I haven't really revised how Alan did this yesterday. But my way of doing this would actually be something very straightforward. But I would rather say that it's kind of brute force. Okay, we really expand all these things out. Okay, to get all the components. Okay, because when we are asked to calculate the Christoffel symbols here, actually there are a lot of components, right? Because remember that we are now talking about three-dimensional space. And then each of the indices here, okay, alpha, beta, and gamma, they all represent three coordinates, okay, r, theta, and phi, right, in this case. Even in the case that when we use the Cartesian coordinates, it can be x, y, and z. So each of the indices here represent three different coordinates, and we have three of them. So technically, we should have 3 times 3 equals to 27 components of the Christoffel symbols. Right? Does it make sense? So what we are supposed to do would be to really write down all of the possible components. Something like, for example, r, theta, phi, theta, r, or phi, r, phi, right, dot, 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 right? So there should be 27 of them. But the trick here is, because the metric we are now looking at has a very nice property that all the cross terms, okay, all the cross terms are 0, okay, we only have the diagonal terms. So we can try to make use of this kind of, symmetry property of the metric to do the calculation better, okay. So what do I mean by that? So, well, the first thing I would like to do would be to really write the Christoffel symbol in a more explicit form. Okay, let's recall the formula here. And recall that I mentioned that there's a one index which is special. Right? It is a contracting index, right? Namely a delta here. Right? The delta here is a contracting index. And whenever we contract in index, it means summation. So technically, we should be able to write something like this. And recall that delta is a contracting index. And because now we're looking at r, theta, and phi, okay? So the summation should run over r, theta, and phi. So now we should have, if we take r as a first index, then we would have r here. And then we have the first term here, something like this. Okay, be cautious that we are now starting to get into the calculation part, okay, which is prone to mistake. It's very easy to make mistakes. Okay, so I encourage you to really check really carefully whether I'm making any mistakes or not. Okay, so now what I'm trying to do is we really expand, okay, really expand the entire summation here. Because we are now contracting delta, okay, which runs through r, theta, and phi. Okay, so this is exactly what I'm trying to do here. So now we're going to run through r here. Okay, theta and also phi here. Okay. Okay, I just noticed the chat. Yeah, toasted 3 times 3 times 3. Oh, okay. You're absolutely correct. Sorry. Yes, this should be 3 times 3 times 3. Thank you very much. Yeah, this is a very low level mistake. Yeah, we have 3 indices, and each index runs from r, theta, and phi, which means there are 3 coordinates. So we have 3 times 3 times 3. 27. Okay. Okay, let's come back to the formula here. I hope that you have the big picture of what I'm trying to do here. Okay. To repeat what I've just done here, I'm just trying to run through r, theta, and phi, because now I'm contracting the delta here. Okay, we go back to the original formula here. Okay, delta here is being contracted, which means that we're doing a summation over all the coordinates, namely r, theta, and phi. So now we have r, theta, and phi here. So if we really diligent enough, we're supposed to write down all these terms here. Okay, theta, gamma, beta, something like this. Theta. Okay, again, it's just my way of memorizing this formula, because the last term here is special with the negative sign. So the contracting index theta in this line, okay, should be here for this last term. And then for the rest of the 2 not so special terms, the contracting index is just one of the 2 indices of the metric. Okay, and beta and gamma is just here. Okay, with different order. And here, if you recall correctly, beta and gamma should be symmetric about each other, okay? Because beta and gamma here, they come from the lower indices of the Christoffel symbol, and they are symmetric. So that's also one of the reasons why I said that beta and gamma is relatively not too special if we compare them with delta, which is contracting index. Okay. So now this is the last big term here. And we are now trying to run the contracting index as phi here. So can anybody quickly tell me what should we write here? Of course, we can quickly say that, okay, that should be g something first derivative plus g something first derivative minus g something first derivative. But where should phi appear here? Again, can anybody quickly tell me? Do you understand my question? You understand my questions? We now have three big chunks of things, okay? Here, when the delta or the contracting index is R, and the second chunk here, when the contracting index is theta, and the last chunk of thing here, where the contracting index is phi. So, okay, nobody answer me. Okay. Let me ask more specifically for the last term here, okay, the most special term here, the minus sign. Where should the phi appear? Okay, Yato said beta gamma phi. Very good. Beta gamma phi. Yeah, very good. Because phi is special here, right, with respect to beta and gamma. So in this special term, it is also in a special position here, namely the first derivative here. What about the rest of the two here? Can anybody quickly tell me the answer? First place. Winky said first place. Okay, I assume you mean that phi, the contracting index, is the first place. Yeah, correct. What about beta and gamma? Okay, yeah, to give the answer. Okay, very good. Beta, gamma, gamma, beta. Very good, very good. Okay, so it seems that you guys have got the big picture about how to do this and how to manipulate the indices in the correct way. Okay, so now let's not forget about what we really want to do in the first place, right? What we really want to do in the first place is to calculate the Christoffel symbol. Or more concretely, what we want to do is to find out each of the 27 components of the Christoffel symbols. But again, as I mentioned, there is some nice property of the metric we can make use of to make the calculation very simple. Okay? And then so-called nice property is that the metric is diagonal, right? All the off-diagonal terms, or the so-called cross term, are zero. So we can quickly observe something here. Okay, we should be able to quickly observe something really useful here. Now look at, maybe let's look at the first inverse metric here. Okay. What this means is we have a specific index here. That's the second one, R. But alpha here is not specific yet, because the alpha here correspond to the alpha here, right? Okay, if I clear this up to make it look nicer, this is alpha, this is R, right? This R is specific, but the alpha here is not yet specific. Right? Can you see the alpha is written nicely? Okay, sorry, my tablet is a little bit slow in sending data. Okay, what I intend to draw here or to write here is this is alpha. Okay. So could you now quickly tell me a special occasion where the whole inverse metric here becomes 0? Okay, I repeat my question. So now R here, okay, the index R here is not 0, right? Obviously. I mean, it's a very specific index, okay? It represents the coordinate R. But on the other hand, alpha here is not specific yet. It corresponds to the first index here, which can run from R theta to phi, right? Although I write delta here, but it's actually also correct for alpha, right? Alpha. So what would be the special case when this G alpha R becomes 0? So Winky said something really instructive. She said the off-diagonal term is 0. Very good. So off-diagonal term, I assume that you mean something like, for example, G theta R or G phi R, right? Obviously, they are off-diagonal, right? And they should all be 0. They should all be 0 because if we recall what the inverse metric looks like here, all the off-diagonal terms are 0, right? But it also means that when alpha is R, okay, this term, okay, this whole chunk of things should not be 0, right? Because if alpha is R, then obviously GRR here is not 0, okay, and the whole chunk of things at the back here may not be 0, right? But what about the second chunk of things and the third chunk of things? If we are talking about alpha being R, and don't forget that for the Christoffel symbol, we have 3 chunks of things here, right? So when we say alpha is equal to R, we must also say that the alpha here is R. Alpha here is also R. So we have this metric being G R theta. And this metric here being G R phi, right? Then what would happen to the whole chunk of things here? What would they become? Okay, that total says 0. Very good. Okay. So what we are going to do in the following session is something like this. Okay, first, let me open a new page. So remember that we talk about when alpha is equal to R, what would happen, and when alpha is equal to theta, what would happen, and when alpha is equal to phi, what would happen, right? So actually what we're going to do is something like this. We consider when alpha is equal to R, alpha is equal to theta, and alpha is equal to phi. Something like this. Okay, I'm not sure why Why my new page hasn't come up yet? Okay. Yeah, 3 big cases. Okay, I hope that you understand what I'm doing now. So let's consider the first case when alpha is equal to r. When alpha is equal to r, what we would get is, okay, first the Christoffel symbol should read something like this. The first index alpha becomes r, right? And then we have the remaining beta and gamma, right? If we recall the formula here, we originally have big gamma and then alpha, beta, gamma. But because now we're considering the case of alpha being r, so we have a small r here on the top here. So we have r, beta, gamma, something like this. And then as we said before, all the alpha becomes r, something like this. And because we're contracting on r, so we can also have something like this. G, r, gamma, beta, okay. Again, these two indices are the non-special ones. And then minus, which is special, and beta, gamma, the non-special one. I guess the special one are here. Okay. And then if we recall what GRR is here, okay, GRR, the inverse metric, okay, is 1 here, right? This is GRR, right? So we come back to this formula, this will become 1. Okay, up to this point, I hope that you guys are not getting lost. Okay, but now we have another problem. So this whole thing here actually have 2 indices, namely beta and gamma, right? Okay, beta and gamma here, beta gamma here, and beta and gamma here. Can you quickly tell me what are the possible scenario for this beta and gamma? This is actually a very straightforward question, but it really requires some really careful consideration. Okay, anybody want to try? We mentioned that there are in total 27 components, and now we are looking at the components when the upper index here is r, okay? But now we have beta and gamma here. And both beta and gamma runs from r to theta to phi, right? So there should be a lot of possibilities here. Okay, nobody answers, but I believe that if you really put the hard works to try to figure this out, it is not very difficult. The first case, okay, the first possibility should be both beta and gamma is r, right? Right. Now we are looking at when beta is equal to r and gamma is also equal to r. This means that we are looking at the Christoffel symbol R components. Okay, does it make sense? Okay, Yato says something really good. both R, both theta, both phi. Either one is R. Okay, very good, very good. So now I'm exactly talking about the first case, okay, that you suggest. Okay, both R. So both beta and gamma is R, which means that we're looking at RRR components of the Christoffel symbol. So now, can you quickly tell me what is the value of these things? Zero. Okay, why? Why is it zero? Okay, GRR is 1, very good. So the trick really lies on this formula here. Okay, or I should say, I should underline this, the whole thing here. We can just quickly kind of substitute R into beta here, gamma here, right? I don't even need to write it down because you can quickly realize that all the indices here are all R, okay? And then what is GRR? GRR is 1, right? As Yato just mentioned, okay? GRR is this one, right? It's just a constant. And the terms here are all derivative, right? The terms here are all derivative. So derivative of constants is 0. So very good. The RRR components is 0. Okay, what about the case when one of the indices, okay, beta and gamma, all right? So remember, beta and gamma here are the not so quite special indices, okay, as compared to the contracting index. And now let's consider one of these indices is R. Let's say beta. But then gamma is not R. So this really means that we're looking at R, say R theta component, or the R phi components of the Christoffel symbol, right? But what are they? Can you quickly tell us what is the value of these two Christoffel symbols components? Let's look at the R theta component first. What would be this term? Can anybody quickly say this? Yato says 0, right? Why is it 0? Why is it 0? Okay, GR theta is 0, GRR comma theta is 0. Very good, exactly. Because if we substitute beta as R, then GRR is 1, which is constant, then the derivative of it is, of course, 0. And the second term here, Yato also told us already, GR theta is 0. So because now gamma is theta, right? Gamma is theta here, and R theta is 0, right? So the derivative of 0 is 0. That would be 0. In the last term here, because we have different beta and gamma now, right? We are talking about, beta is R and gamma is not R. They are different. And as we said, the off-diagonal components of the metric is 0, right? And of course, the derivative of 0 is 0. So this is also 0. So we can safely say that the RR theta components of the Christoffel symbols is 0. What about this one? If gamma is phi, what would happen? Can anybody just do it very quick? You know, I should call this kind of gymnastic, right? A quick gymnastic, okay, of quickly substitute R and phi into this formula to get the answer. Okay, that also says 0. Okay, very good. That's actually correct. Because again, GRR is constant, the derivative is 0. And then for the second term, we have R phi, right? G R phi. G R phi is 0, so the whole term is 0. And then G R phi, comma R. But G alpha is 0. So it's also 0, right? Yes, very good. And actually, there's another thing I would like to mention is that I actually have mentioned this before, is that beta and gamma is symmetric, right? So when I say that the RR theta component is 0, we can also safely say that the R theta R components is also 0. And here, it means that the R phi R component is also 0. Okay, because beta and gamma is symmetric of each other. So even when we consider the case when beta is not equal to R and gamma is equal to R, we should yield the same results. Okay, so this is why we have this result here. Okay, what about the third case where both beta and gamma is not R? Okay, something like this. Okay, so please come out. Where's my new page? I actually don't quite like this slow response of my tablet. Yeah, because actually I have already opened a new page. Yes, okay. Okay, the third cases are both beta and gamma are not equal to R. Okay. So for the interest of time, I won't really ask you what would be the possible scenario. Okay. But if we are really careful enough, we should have something like this. Okay. Beta equal to phi, gamma equal to gamma to theta. Okay, this first two case means that both beta and gamma are not R, but they are different from each other as well. Okay, one of them is theta and one of them is phi. Okay, but for case 3 and case 4 here, what I like to say is they are actually equal. Okay, whether both of them are theta or whether both of them are phi. So now what we really need to do is just look at this equation again, okay? And then really substitute the different indices here to see whether we can quickly get 0. Okay, if we can quickly get 0, then we would be very happy, right? Because that's really easy to deal with. So let's quickly do this. Okay, if beta is theta, then the first term here should be 0, right? because our theta here, G our theta is 0, so it's 0. For the second one, we have G our phi. G our phi is 0, so it's 0. And what about the third term? Okay, the third term should also be 0 because we would have G theta phi, right? And G theta phi is also an off-diagonal component. So we can quickly say that if beta is theta and gamma is phi, then the components of the Christoffel symbol is 0. Okay. So the second case is the reverse. Okay, beta is phi and gamma is theta. Okay. Well, actually, by symmetry of beta and gamma, we can also say that this is 0, right? Because these two are equal, right? But what about these terms here, or this case, when both beta and gamma is theta? What would happen to the first term here? Okay, the GR beta, comma, gamma. Okay, what would happen? We actually have GR theta, right? For the first term, GR theta, which is 0, right? Because it's off diagonal. For the second term, we have GR theta as well, because beta and gamma are the same, right? So gamma here is theta and GR theta is 0 as well. But what about the third term here, the last term here? We have G theta theta this time, right? Beta and gamma are theta, and G beta gamma here becomes G theta theta. But G theta theta is not 0, right? If you recall G theta theta here is R square here, right? Or if you look at the line element, the G theta theta here is the coefficient of the d theta squared term, and the coefficient of d square or d theta squared term is nothing but R squared, right? So this is something special. It is not 0. Okay. First, we look back this formula. Okay. Don't forget the 1/2 here. Okay. It's very tempting for us to forget this 1/2 here. So we write the 1/2 here. Okay. And then GR here is 1, which can be ignored here. And the first term and second term, as we mentioned, is 0. The last term is not 0. Okay. It's minus G theta theta comma R, right? Which is something like this. G theta theta is R squared, right? So if you're quick enough, you should be able to get this is something like this. Right? So now we got the first Christoffel symbol component, which is non-zero here. Okay. It's non-zero. Okay, does it make sense? Are you guys still following? I hope you're still here, you're still alive. I know it might seem a bit, annoying at first with all this kind of, indices and calculation, but I hope that you can get the big picture here about the calculation. So now what about the last case here? Beta gamma is equal to phi. Obviously, we are calculating R phi here. Okay, R phi component of the Christoffel symbol. Okay, actually, I would like to give you like 1 minute to compute these things out for me. I can assure you that this is not 0. But what I want to do is give you 1 minute to try to get the answer for this one. Okay. Okay, I would wait until 3:26. Okay, 3:26. Or actually 3:27. Okay. I will restart at 3:27. Okay, to give you some time to try this out. What is the R55 component of the Christoffel symbol? If we look at this formula. Okay. Anybody? Is 27 already? Winky said minus R sine square theta. Okay, very good. This is actually the answer I have derived for myself. Yeah, very good. Yeah, so this is the R55 component of the Christoffel symbols. Yeah, very good. I hope that you have obtained the same results here. Okay. Very good. Thank you, Winky. And Jorge, you got it shortly after. Yeah, very good. Very good. Okay, it seems that all of you have made use of the G55. Okay. You know what exactly G55 looks like. And make use of this formula here. Sorry, the 5 here should be lower indices. Okay. Okay, I'm not sure. I don't know why my upper indices is not erased yet. I have erased the. Okay, good. Okay, very good. So you guys have already arrived at this point, which means that we have calculated all the possible cases for when alpha is equal to R, okay? But unfortunately, we still have 2 big cases left, namely when alpha is equal to theta and alpha is equal to phi. Okay? But for the interest of time, because we only have like 30 minutes left, so I won't really go into the details of calculating the Christoffel symbol for these 2 big cases. What I can do here is just to give you the answer that I have derived. Yeah. So alpha equal to theta and alpha equal to phi. Okay. Alpha equals theta. Okay, so for alpha equal to theta, the only non-zero components would be this guy here, okay? I really strongly encourage you to try this out for yourself after the intensive class, okay? And then it's equal to 0 otherwise. Otherwise here means that for beta and gamma not equal to theta and r here, okay? And for alpha equal to phi case, the only non-zero term would be the theta phi phi, and this is something like this fix. Okay. Maybe this has been worked out yesterday. I'm not sure, but I really encourage you to do it for yourself, because this is a very good exercise to work with the indices and so on. Okay. And again, this is for beta and gamma. Here. Okay. Winky said Zoom's always delay. Oh, yeah, right. Yeah, but I think my delay is mainly due to my tablets, because I'm linking my tablets to an app on my laptop, and it seems that there is some delay between the device and the apps. Anyway, yeah, this is what we have done for this question. Okay. Okay, we have gone a long way. So let's go to B3. Okay, we have done a lot of things for B2. Okay, for the Christoffel symbols. Now let's quickly move on to B3. Okay, question B3. So now we are supposed to calculate the components of the Riemann tensor. Okay, what would you say about the Riemann tensor here? Can anybody answer me? If you are asked this question, what would you say about it, the Riemann tensor? Okay, B3. What is the R beta gamma delta? Anybody? Anybody want to try? Okay, actually, I would like to give you a multiple choice. Who will say that Riemann tensor in this case is not zero? Okay, Yato in the chat box said Christoffel symbols and derivative of Christoffel symbol. Okay, I assume what Yato means is that you want to really calculate the Riemann tensor by brute force. Okay? You make use of the formula for the Riemann tensor, which really involves a lot of Christoffel symbols. Yes, that's one way to do it. Okay? Really, it's really a legitimate way to do it. But what about other people? Winky said me. Oh, sorry, I forgot what I asked. Did I ask, do you think it's non-zero? Okay, Yato said not zero. Chuck Singh said non-zero, and Winky said non-zero. Okay, almost all of you said that the Riemann tensor is not zero, right? Okay, why? Why? I didn't put this in the questions, but I would like to ask you here why you think it's not zero. Winky said because sphere surface is curved. This statement is correct. Okay, sphere surface is curved is correct, but don't get this wrong. Okay, for this question, we are actually considering the three-dimensional space, the Euclidean three-dimensional space. The sphere it just comes in when we look at the coordinates, okay? Because we are using spherical coordinates for our works here. So technically we are not really looking at the sphere. Okay? The sphere is just a tool for us to, to span the coordinate systems in the space that we're interested in now, namely the Euclidean space. Okay. So yeah, so you're absolutely right that sphere surface is curved, but this is not what we are looking at in this question. Well, actually, that is the next question, question 3. In question 3, we will be looking at the surface of a sphere. But in this case, we're looking at the space. Okay, so Winky said it should be, the Riemann tensor should be non-zero because we are looking at the sphere surface, but I've explained it's not the case. What about Chuck-Sing and Yato? Both of you said that the Riemann tensor should not be zero. Why? Or have you changed your mind now after I've explained to Winky that we are actually looking at the space? Okay, Chuck-Sing, you don't know. It's okay. Okay, Leon said, I'm going to guess it should be 0 because we are still in flat space. And Winky says 0 then. Okay, Leon actually has mentioned the reason why Riemann tensor in this case should be 0. Okay, very good. It should be 0. Okay. Forget about this. Riemann tensor should be 0. And the reason is exactly what Leon just mentioned, because we are looking at the flat space, right? No matter what coordinate system we are using, the space itself is not affected by the coordinate system, right? Because the coordinate systems is nothing but just some artificial tools that we put in the space to do the calculation, right? So the curvature of the space itself should not be affected at all by the coordinate systems, right? So if you're looking at the flat space, then of course, the Riemann tensor should be 0, right? And then some of you may ask, oh, wow, but you said that Riemann tensor is calculated in terms of some Christoffel symbols, right? Something like this, right? Oh, this should be minus, sorry, plus gamma, gamma, right? But obviously, we have some non-zero Christoffel symbols, right? When we do the calculation for the Christoffel symbols, making use of the spherical coordinates, right? Well, actually, it turns out that even when some Christoffel symbol here are non-zero, the Riemann tensor here is 0. Okay. Actually, we can try some example here. I would like to just try, say, R theta, phi theta. R theta. Okay. These are some suggested components of the Riemann tensor that you can try. But of course, you can try any combination of indices. Okay. Because each index here runs from it runs over 3 coordinates, right? And now we have 4 indices. So we should have 3 times 3 times 3 times 3 equals to 81 components for the Riemann tensor. So technically, we will need to calculate all the AT1 components of the Riemann tensor. But of course, as you may have guessed, due to some very nice symmetric properties of the Christoffel symbols and the metric, the independent component actually is not as many as 81 components. Okay, so I'm not talking about an independent component here. But what I'm trying to say here is that technically we can try all the possibility here for all the components of the Riemann tensor, but we can just example here, okay, trying to calculate all this. So because we don't have enough time, I think I will just try one of them here. Let's look at the R. R theta, phi theta. Okay. Still hate the delay. Theta, phi theta. Okay. So, what is the Riemann tensor here? Here. So as Yato said that we can make use of the Christoffel symbols, right? We call the formula. If I'm not mistaken, we should be able to get something like this. Phi theta plus phi sigma theta theta minus r theta lambda phi theta. Okay. I'm not going to check this. I hope I'm correct. Now, let's look at this explicitly. What is the R theta theta component of the Christoffel symbol? R theta theta. Okay, if we recall the result that we have got before, it should be minus R here, right? Okay, so R theta theta component of Christoffel symbol is minus R. But what about the derivative of minus R with respect to phi? What is it? Winky, I will come back to your question later about the trick to remember this. But what about the first term here? Again, R theta theta components minus R. And now we're going to take the derivative of this minus R with respect to phi. What is the result? Winky says 0, correct. 0, right? Because R and phi are independent coordinates. And when you differentiate the coordinates with respect to some other coordinates, you will always get 0, right? What about the second term here? R theta phi. R theta phi components of gamma, I mean the Christoffel symbols. Because of the time, the limited time, I won't really check very carefully. But if you double check for me, actually we don't have this term calculated before because it's zero, right? We just calculate the non-zero components of the Christoffel symbol, which means that all the other components, okay, with a different combination of indices should be zero. So because the r theta phi components of Christoffel symbol itself is zero, then when you take the derivative with respect to theta, it's nothing but zero. Okay. Now we have come to something tricky, okay, this term. And remember, okay, these two indices is actually contracting about each other. Okay, well, actually, let me do this. I actually have summarized all the non-zero components of this Christoffel symbol. I think that would be better for me to write them all out for you in one page. Please excuse me for copying all these things. And actually, I strongly encourage you to double check all this by yourself. This is really a good exercise for you to do the calculation. Okay. Cotangent theta. Okay. These are all the non-zero components of the Christoffel symbol. So now let's look at the term again. Is there any nice property that we can make use of? Okay, when we're given all these non-zero components here, so that the whole thing becomes zero. Because again, we now having the contracting indices here. Okay, it's contracted. So what does it mean? It means summation, right? So we have the so-called R case, okay, and the theta case, and also the phi case. I hope you get what I mean here. I'm omitting all the indices here. Okay. But what I really want to say, here is actually exactly the same as what we have done before. We are doing summation here, so we have actually three terms here in just one single expression here, right? But because these are the only non-zero terms for the Christoffel symbol, so there should be something really nice about this, so that some of these things are zero. Okay, so what can you say about this? So the first thing we notice is that this is theta, right? What is the only possible thing up here, down here, that this does not become zero? Do you know do you understand what I mean here? The term that I want to calculate is the whole chunk of things here, which actually is the sum of this thing here, and this thing here, right? Because sigma here is contracted. and sigma runs from r, theta to phi. Okay, which means that sigma here can have three possibilities. So among the three possibilities, r, theta, and phi, which of them are non-zero? Considering the non-zero terms here, given here. Do you understand what I mean? Only the r term, exactly, right? So the r theta theta term, okay, here, right, is the only non-zero term for this one, right? So the sigma here, okay, although I just mentioned it has three possibilities here, the possibility that r equal to theta and r equal to, sorry, not r, but sigma here, sigma equal to theta or sigma equal to phi should vanish, right? So we only have the r term here, r, right? And also this one should be r as well because they are contracted. Okay. So this is the only possible non-zero term for the third term here. But what about the first term here? What is it? Can you find it down in the list? Yes or no? Yes or no? My question, okay, if I repeat my question, I'm asking, okay, we have a r phi r term here, r phi r component of the Christoffel symbol here. Can you find it in the list here? We have r at the top. We have r at the top, but we only have two terms with r at the top, namely this one and this one. And none of them have phi r down there, right? So Winky also said no. Yeah, very good. So although we suspected that this term is non-zero, the first term is zero. So this whole thing vanishes, becomes zero. But what about the last term here? Again, if you remember, these two indices contract. Okay, the lambda here contract, which means that it's again a summation. Okay, something like this at the top here. Right? But again, if we observe carefully, we can only set lambda as theta here, right? Because we have r here, and for the Christoffel symbol components which have r up here, we only have theta theta and phi phi here. So in order for this term to be non-zero, we only have lambda equal theta, right? It can't be phi, right? Because we don't have theta phi down here, right? So lambda should be theta, okay? So lambda here is also theta. But what is the theta phi theta term here? Okay, this term here. Well, please excuse my ugly drawing again. But I'm asking the theta phi theta component here. Can you find it down the list? Okay, Winky said no. So happily, okay, the last thing here is also 0. So happy ending. The Christoffel symbol, if we just calculate this component, is 0. Okay, so this really verified partially that our claim that the Riemann tensor should be 0 is correct. But of course, there are a lot of work to do, okay, to really try out all the possible indices here, the combination of indices here. I actually have personally tried these two here, and you are also strongly encouraged to try this out for yourself. But actually, there's another point I want to make. Okay, actually, if we study GR well enough, okay, we don't actually really need to verify that all the components of the Riemann tensor in the spherical coordinates are all 0. Why? Because where's my new page? Because in question A3, okay, in A3, remember, we have calculated the Riemann tensor, right? It's 0, right? So now we just transform the coordinate system, okay, from x, y, z to r theta phi. So now we are talking about question B3 here, right? So this is nothing but a coordinate transformation. Okay. And if we study GR well enough, we should notice as a fact that whenever you have a tensor and is equal to 0 in some reference frame or coordinate system, then it will imply that it's 0 in all coordinate system. Okay, this is very important concept in GR. And this is exactly why we want to deal with tensor, okay? Because tensor has this nice property, okay? Okay, because tensor obeys some sort of transformation rules, okay? I hope that you remember how to transform properly a tensor when we transform the coordinate systems. But in a special case where tensor is 0, okay? When it's 0, then it would be 0 in all coordinate systems. Okay, so this implies that if we have the Riemann tensor being 0 in the Cartesian coordinate, it would also be 0 in the spherical coordinates. Okay. I use the prime here to denote that it is transformed property. Okay, transformed. Okay, so actually for this question B3, we have two ways of answering this. The first way is just by brute force, okay? Just what I have just shown you here. And the second method is actually just by this argument, okay? Because we know that Riemann tensor is a tensor, and tensor has this nice property that if it's 0 in some coordinate system, then it would be 0 in all the coordinate system. Okay, no matter how we transform the coordinate system, it would be 0. So it's 0 also, even if we use the spherical coordinates. Okay, so I hope that you understand why I want to show these two ways of doing things. The last thing, of course, is the most, you know, is the wisest way to do this. Okay, is the simplest argument. Okay, but even for this method, okay, by brute force, my stand would be it's also quite meaningful to do this with you here. Because you can, you know, get a feeling of, you know, how to calculate the Riemann tensor by brute force, okay? Because we are lucky in this question, okay, that Riemann tensor is 0 in all the coordinate systems, but in some cases, the Riemann tensor may not be 0, and in that case, maybe we really need to do all this kind of calculation to calculate the components of the Riemann tensor. Okay, so sorry, I really have to overrun because now it's already 4 o'clock, but I still have two important questions here, C1 and C2. Actually, the whole point of doing this question 2, at least from my point of view, why I designed this question 2 in this way is I want to get to C1 and C2. So if you allow me to continue to C1 and C2, so please stay around with me. But of course, if you have some other schedule, you have to leave now, and please feel free to leave. Okay, C1. Okay, I really want to finish C1 and C2 first, at least for this session. Okay, so C1. Okay, it asks, can we conclude that the space, okay, or the manifold in general is flat if the Christoffel symbols are 0? And conversely, can we conclude that the Christoffel symbols are all 0 if the space is flat? Okay, actually it contains two questions. Okay, the first question is if the space is flat, can we conclude that sorry, let me rephrase the question. If the Christoffel symbols are 0, okay, can we conclude that the space is flat? Okay, can anybody quickly answer this question? Do you understand the question? No. Okay, Winky said no. Yato also said no. Okay, maybe let me write this down explicitly. The first question is, can we conclude that the space is flat if the Christoffel symbols are 0? So what this really asks is, if we have the Christoffel symbol 0, can we imply that the space is flat? So now, Yato said no, Winky said no. Chuck Sing asked, is it all 0? Okay, sorry, I should explain this more explicitly. When I say that the Christoffel symbols are 0, I mean all the components are 0, right? Okay, all the components of the Christoffel symbol are 0. Okay, So here I mean all components. So if the Christoffel symbols have all the components being 0, can we say that the space is flat? Chuxing is saying that, okay, yes, it's flat. Winky said if the derivatives are 0, then it is flat. Li Yong said yes intrinsically and no extrinsically. Well, actually, I think you guys are getting it correctly now. The answer is yes. Yes. Okay, so no question mark here. It's really the correct implication here. The argument is really simple because if the Christoffel symbols are all 0, then the Riemann tensor will be 0, right? Right? Does it make sense? If we recall the formula for the Riemann tensor, this one, okay? If all the components of the Christoffel symbol is 0, then obviously the first two terms 0 because the derivative of 0 is 0. And even the last two terms, they're all 0, right? Because products of 0 are zeros. So the Riemann tensor is 0, and this is nothing but just saying that the space is flat. Okay, is it clear now? So for the second part of C1, conversely, okay, I said conversely, can we conclude that the Christoffel symbols are all 0 if the space is flat? Okay, now I'm actually talking about the converse thing, okay, the reverse thing. We were just saying that this condition, okay, would imply this condition. But what about the reverse? Does flatness imply that the Christoffel symbol have all the components being 0? Which is the other way around, okay? In the first part, we are talking about this direction, okay? This direction. But now we are talking about the other way around, like this. Okay, so Winky said no, Vincent said no, Chuxing also said no. And Winky gave a very good reason. They said they can cancel each other to give 0R. They can cancel each other to give 0R. Right, I think I know what you're saying here. Yeah, but actually for this particular question, we already know from our previous results that the answer is no, right? Because if we recall, if we use the spherical coordinate system, okay, r theta phi, then although the space we're talking about is the good old Euclidean flat space, the Christoffel symbol is not 0, right? As we calculated before, the Christoffel symbol is not 0. At least they have some non-zero components, right? So yes, this implication is actually not correct. We should put a cross here. The flatness does not imply that the Christoffel symbol are all 0 for components. Okay. And physically, the reason why the Christoffel symbol can be non-zero is because the coordinate system itself is actually changing, right? is changing from place to place. And by saying changing from place to place, what I mean is the basis vector, okay, the basis vector defined at every point in the manifold really differ from each other, right? Because if I draw the two-dimensional case using the polar coordinates here, the basis vector, for example, at this point, would be something like this. Right. This is ER, this is E theta, right? If you recall. Okay, and I'm supposed to have this ER coming from the origin. But for this point, ER points this way, and the E theta points this way, right? So obviously, this basis vector is not the same as this basis vector, right? Although they are the same ER, right? Similarly, E theta here is not the same as the E theta here. So I can say that the basis vector wiggles around, okay, around the whole space if we use this kind of coordinate systems. And that's why we can get the Christoffel symbol not being zero for this case, although the space is flat itself. Okay, so this is a point that I really want to make here for this question. Okay, so let's move on to C2. Okay, C2 asks, okay, can we conclude the space or the manifold is curved when the Christoffel symbols have non-zero components? Okay, this is the first part of the questions. Okay, what do you guys say? Okay, Lee Yong say no. Winky say no. Okay, very good. Yes, the answer is no. Okay. If we have Christoffel symbols not being zero, okay, still we cannot say that the Riemann tensor is not zero, right? Which means it's curved. Right, very good. Again, this is exactly what we have just seen for this question. We have non-zero components for the Christoffel symbol when we use the spherical coordinates, r theta phi. But the space is not curved, right? Yeah. And actually, this statement, okay, if you're familiar with logic, okay, this is nothing but the second part of the last question here. So there we have the flatness does not imply the Christoffel symbol being zero for all components. If we negate both of this condition and then do the reverse, okay, here, which means that it's not this condition and not this condition, and not this condition exactly means the Christoffel symbol is not zero, and the negation of this flatness here, okay, is exactly the curve condition here. Okay. And because this statement doesn't hold, then when we negate both of them and then do the reverse, it's also not true. Okay. I hope you understand what I'm talking about. I'm just talking about the logic, okay, the implication, like when A implies B, it means that a not B implies not A. Okay. So what I'm doing here is just the negation version of the statement, okay, because now I'm talking about A here does not imply B. So not B does not imply not A either. Okay. Okay, so this is the first part of C2. What about the second part of C2? In the second part of C2, I'm asking, must the Christoffel symbols be all 0 in the curved space? Okay, Lee Yong's mentioned, is asking for the second part, do you mean all 0 or all non-zero? I think you are absolutely right. I think that my initial intention for this question is asking, must the Christoffel symbols all sorry, okay, I should ask this better. I'm asking, must the Christoffel symbols contain some non-zero components in the curved space? Sorry, I think I have made a typo here. I think Lee Yong got my point here. Okay, for the second part of C2, I'm asking whether a curved space-time or space or manifold or whatever. Okay, and of course it means that the Riemann tensor is not 0. Okay, does this imply that there's some components of the Christoffel symbol being non-zero? Yeah, this is exactly what I want to ask. What do you think? Yes or no? This is a bit away from what we have discussed. Yeah, actually, we haven't covered this case yet because we're not talking about curved space yet, right? Okay, Lee Yong said yes. Okay, there should be some non-zero terms, and Winky said yes, it contains non-zero parts. Yes, I think you guys have done a very good job. My answer to this question is yes. In general, okay, there should be some non-zero components of a Christoffel symbol. Okay, because if you have a non-zero components of the Riemann tensor, okay, then if you consider the formula for Riemann tensor, when the Riemann tensor is not 0, then in general, there should be non-zero components of the Christoffel symbol as well, right? This is one way of looking at this. But the other way around of looking at this is that, again, it's about the logic, okay? Is the negation, or is the reverse version of the first statement here that we have done for the first part of C1. Okay, so in C1, we said that gamma equals 0 implies flat, right? This is what we have done, right? So if we negate both of the condition, we said not flat, and then not Christoffel symbol equals 0, which means that the Christoffel symbol is not 0. And then we can do the reverse. Okay, so curved space-time or curved manifold indeed implies that there's some non-zero components of the Christoffel symbol. Okay, so and this is exactly what the second part of the question is asking. Okay, so this question mark is going away. The answer is yes. And I hope that this two sub-question, okay, C1 and C2, have given you a clear picture or clearer logic about what it means when we have the Christoffel symbols, zero or non-zero, and the Riemann tensor being zero and non-zero, and what we can say about the curve nature of the space-time, whether it's flat or curve, given the Christoffel symbol and the Riemann tensor. Okay, okay, I think I have really done a very bad job in the time management. It's already 4:20 something. I apologize. But we still have one more questions. Okay, I think here I can just offer to whether to continue or not. Okay, and actually, Winky, I still remember I promised you to mention how I remember the trick. What is the trick to remember the formula for the Riemann tensor? Okay, I can answer this after this. But now I just want to make an offer. I can continue, okay, to answer Winky's questions, and also continue to question 3. But I need your vote, okay? Is there anybody who strongly wish to continue to question 3 today? Okay, Winky said yes, please. Okay, okay, that's my pleasure to continue. But again, because it's already overrun, so I totally understand if you have any other schedule. So you may want to leave now. I don't mind. But okay, so let's move on. Or actually, do you guys want a break? Because I have been non-stop, like for 2.5 hours. Do you want a 3 minutes or 5 minute breaks? Okay, Winky said that would be cool. Okay, then let's have a break. Maybe let's come back around 20, okay, maybe 28 past 4. Okay, okay, see you in a bit. Okay, welcome back. Sorry, I a bit late. It's 29 already. And I hope that all of you guys have come back. So, okay, so let's get back to the rest of what we want to discuss today. Okay, so first of all, I'd like to address to answer Winky's question about how I remember the formula for the Riemann tensor. Winky, I hope you have already come back. So, yes, okay, very good. Okay, well, my trick is actually is not really called a trick. I just try to remember it by brute force. My way of doing this is that, okay, first of all, of course, I remember the big picture first. It's something like this. And then this is the first part of the formula. And then we have the second part of the formula as something like this. Okay. And then I would remember for these two terms, okay, remember these two terms is having an indices like this way. First, I would group the alpha beta as something, I won't say similar, but I would make it as a group. Okay, alpha beta is a group. That means that for the first two terms here, I would have the alpha beta right away like this. Okay, and then for the rest of the indices, namely mu nu here, okay, I need to substitute this mu nu into this slot here. Okay, and obviously it can either be mu nu or nu mu, right? And the order would be, first I reverse the order here, namely nu mu. And then remember that the nu mu here is the first, is the indices here of the first term. And then the second term would be mu nu. Okay, I hope that you have got the big picture. Okay, so the alpha beta is something fixed here. Okay, the same as alpha beta here. So the rest is just the order of the mu nu here. Okay, either mu nu or nu mu. Okay, and I don't know why, but the first term would have the reverse order first, namely mu mu. Okay, and the second one is the normal order mu nu, something like this. Okay, so this is the reverse first, namely nu mu. And here is a so-called normal order mu nu. And actually, I have abused the use of the term normal, because it's really not correct to say that mu nu is the correct order or the normal order. Okay, there's no such thing. But I'm just talking about this with respect to the order here originally in the Riemann tensor. Okay, if I call the original order here as normal, then the normal order comes to the second term here. This is how I remember the first two terms. Then we have the second term here. Okay. And for better looking, I would write the term here instead. So again, for alpha beta here, okay, the so-called fixed indices here, I would first write something like this: alpha beta, alpha beta. Okay, I will just write this right away. Okay, the very or I should say the leftmost index here and the rightmost index here. Okay, they are already occupied by the two fixed indices here, alpha and beta. And then I will remember that both of this term would have a contracting indices. Okay, whatever you call the contracting indices, because it doesn't really matter if contract indices. Maybe you would call this sigma, and call this, and the same here, but I would rather use lambda. Some books would use the same symbols here. So instead of lambda, they would also use a sigma here. But I'm using lambda here just to emphasize that they are talking about different things. They are different terms. But actually, it's also okay if you use sigma instead of lambda here. Okay, so they're contracted. So now what's left is again mu and nu, right? Right, because now we have this slot, this slot, and this slot. We only need to fill in mu and nu in these two slots. And this time, in contrast to what we have just do for the first two terms, the order is actually like this: mu here, and then nu here, mu here. So in terms of the languages that we have defined here, we actually have the normal order first, and then the reverse order. So they are different. Okay, the first two terms and the last two terms has different order regarding the order of mu and nu. For the first two terms, you have the reverse order first, but for the last two terms, you have the normal order first. Okay, this is how I remember this formula when this formula is not given in the cheat sheet or the formula sheet. Okay, it's just my way to remember this. Of course, you're welcome to have your own way of remember things. But I hope that even by explaining how I remember these things, I can give you a picture about how to manipulate the indices. Okay, how is it like to work with this kind of indices or tensor things. Yeah. Okay, so hope that this is instructive to you. And let's move on to the last question of the workshop. And I hope that I can finish this within 20 minutes so that we can end this workshop before 5 o'clock. Okay, the last question asks about a totally different space. Okay, for the first question, we are looking at a cylinder. The second question, we are looking at the normal space, okay, the Euclidean space. And for this last question, we actually consider a sphere, okay, a sphere of radius a. Okay, the first question, is this surface flat or curved? And again, I'm asking from the perspective of intrinsic curvature. Is it flat or curved? Can anybody quickly answer? Okay, Leo said curve. Very good. Obviously, it's curved, right? And actually, it's the most typical example we use when we introduce a curved space, right? Okay, now part B. Do you expect the Christoffel symbols and the Riemann curvature have all of their components being zero, or some of them are non-zero? Winky said non-zero terms. Okay, are you talking about the Christoffel symbols or the Riemann tensor, or both? Okay, you said Riemann tensor. Okay, good. Riemann tensor have Riemann tensor has non-zero terms or components. Okay, what about Christoffel symbol? Winky said both. Is there anybody who disagree or agree? Chuck Singh says some of them are non-zero. Okay, do you mean the Christoffel symbol or Riemann tensor? I'm asking about two different quantities here. Chuck Singh said Christoffel symbol. Okay, have non-zero. Good. Actually, Chuck Singh has answered the other part of the question, okay, about the Christoffel symbol. Yes, you guys are absolutely right. The Christoffel symbol also have non-zero components. And actually, this can be easily deduced from what we have just discussed, right? Because now we are dealing with a curved space. And we just discussed the curved space implies that the Riemann tensor is non-zero. And it also implies that some components of the Christoffel symbol are non-zero, okay? So this actually is just a review of what we have discussed. Okay, now part C. This is where the calculation comes in, okay? Write down the metric of a spherical surface with radius A, okay? And hence compute the Christoffel symbols and the Riemann tensor. And here I specify the components to be R, theta phi, theta phi. Okay. Because I expect that I won't have time to do all the components, although I have already overrun. Okay, but let's do that. Let's do the metric first. Can anybody quickly share what is the line elements of the sphere? Anybody? Actually, this is even simpler than the spherical coordinates that we saw in the last question, because now we are dealing with just two-dimensional surface. Okay, excuse my drawing. And when we're talking about two-dimensional space, what we are talking about here is actually some kind of area like this. Okay, and this and this. Okay, can anybody quickly tell me what is this part? This distance? Chuck-Sing said AD theta square. Right. Chuck-Sing is correct. It should be something like this. Okay, very good. The reason is because this part is nothing but AD theta, and this distance is A sine theta d phi. Okay, I hope you have got this right. This should be not very difficult. What about the metric? Because whenever we're dealing with Christoffel symbols, Riemann tensor, we almost always start from the metric. So with this line element, okay, what we can have, okay, would be something like this, right? Right, 0 here and 0 here. And again, for the inverse metric, we actually have done this before, okay, very similar. But just to save time, I would just write the answer here. Okay. It's just an inverse, right? It's just an inverse of the metric, so that the matrix multiplication would give the identity matrix, right? So now we should compute the Christoffel symbol. Well, actually, this is very similar to what we have done for the previous questions. Okay. So, okay, so let's see how much you remember from our last question. So, okay, maybe let me open a new page. Okay, what I do here would be I really hate this slow response. Where's my new page? Sorry, guys. I just want my new page to appear. Okay, here. Okay. So let me try to quickly write this down. Okay. Again, my way of remembering this is we have the top index here as alpha. So after writing the 1/2, okay, which people may forget very easily, 1/2, and then the inverse metric G, and then alpha, okay, keeping the same top index. And then it comes the contracting index, delta, okay, and then we have something like this, right? Minus, okay. So now we need to play around with beta, gamma, and delta, in which the delta is the so-called special one, right? Because beta, gamma is symmetric. They're kind of belonging to the same group, and delta is kind of special, okay? So it should go to this special term as the derivative, okay? This contracting index should go to the derivative of the last term, and then this position in the first two terms. Okay? And then the rest is just the beta and gamma. The beta and gamma is symmetric, so I don't really care which order is which. Okay, so something like this. Okay, and then again, delta is contracting, right? This is contracting, 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 contracting. And now we are dealing with a two-dimensional space, and the coordinate system is theta and phi, right? That means this delta, okay, the contracting index, also runs from theta and phi. So we should be able to write something like this. Okay, we replace every delta with theta. Okay, keep the gamma and beta. Beta, gamma, and then this is theta. Okay, but the summation has not ended yet. We have just done the theta part. We still have the phi part. So we should have something like this. Phi, beta, gamma. Okay, again, we keep we replace with phi, okay, and keep the gamma and beta. Beta, gamma, and phi here. Something like this. Right? Now, if you recall what we have done for the previous question, in which we consider 3 cases, right? And the 3 cases depends on what value this alpha here, okay, the top index here holds, right? But in this case, we don't need 3 cases. We only need 2 cases, right? Because each index just runs from theta to phi, okay? So we only have either alpha is phi or alpha is, sorry, whether alpha is theta or alpha is phi. Okay, we need to consider these 2 cases. Okay. So what about when alpha is theta? Okay, when alpha is theta. Again, when we look at this formula we have just written down, we actually don't have this line anymore, right? The second line here, okay? The second line will vanish, right? Because if alpha is theta, then we would have g theta phi for the first metric here, which is a cross term, right? Which is an off-diagonal term. And we have derived that even for the inverse metric, the off term is 0, right? So the second line will vanish if alpha is theta. So we only have the first line left, right? Does it make sense? So we would have the Christoffel symbol. Alpha now is theta, okay? And then beta, gamma, and then equals to the first line, g theta theta. Oh, sorry, I'm writing here. Okay. And then g theta beta gamma, g theta, and then gamma beta, minus g beta gamma theta. Okay. And then the second line vanish, right? For the reason I just explained. So now we have again come to the point where we can consider different possibility for beta and gamma, right? Because now what we have, what we are left with is the beta and gamma, right? For this formula, okay. We just need to play around all the possibility that beta and gamma can take. So there are, in general, 3 possibilities. Beta and gamma are the same, which is equal to theta. Beta and gamma are the same and is equal to phi. And then they are not the same. Okay, one of them is theta and the other one is phi. Okay. So what happens if beta and gamma are both theta? Which means we are talking about the theta, theta, theta components. So first, G theta theta here is what? It's a constant, right? Because if you look at the coefficient in front of d theta square is a square. And this is nothing but g theta theta, right? G theta theta is a square, which is constant. Okay, and whenever we have constants, we'll be very happy because everything will go to 0. What about when beta and gamma is equal to phi? Then we have the Christoffel symbol and then theta, phi, phi. Okay, what would we get? Well, actually, we can quickly, okay, I noticed that Kwok Hei mentioned if I knew such an efficient method, I would have finished my midterm on time. Well, yeah, it just requires practice. Okay, if you are familiar with this kind of indices and be careful enough, then you should get the gist of how to compute things. Okay. For example, for this one, now we are looking at theta phi phi components. And actually, we can quickly realize that these two terms would become 0, right? Because we have theta as the first index, but now beta and gamma is phi, which means that this index and this index are not the same as theta, right? Which means it's a off-diagonal component, which means it's 0, right? But what about the last term here? Beta and gamma is the same, which is phi. So we have g phi phi. G phi phi, and then take derivative with respect to theta. So let's look at what g phi phi is. Oh, g phi phi is something like this. Okay, we now get a little bit unhappy because it's not entirely constants. Okay, we have a squared, but we also have sine square theta here, right? So it's not a constant. And what makes things worse is that the derivative that we are now taking is with respect to theta, right? And it really contains theta here. So we can't just say that the whole thing is 0, okay? This whole thing is obviously not 0. So the answer for the theta phi phi components would be, first, we have the 1/2, okay? Don't forget the 1/2. And then g theta theta inverse, which is this thing here, right? 1 over a squared. 1 over a squared, right? And then the bracket, okay, the first two things is 0. But the last thing here is, first we have minus sign, and then it's nothing but something like this. Okay. And then what's left is just some, high school mathematics. G phi phi is a square sine square theta, right? It should be something like this. Because it's just high school mathematics, I won't waste time to ask you questions. This cancel. And then what we have is like 2 sine theta cosine theta equal to minus sine theta cosine theta. Okay, so this would be our first non-zero component, theta phi phi. Okay, something like this. What about this case? When they are different. Okay, if we look at this very quickly, the first term is 0, right? Because when gamma is phi, it means that we are taking derivative with respect to phi. But we remember that there's no phi in the metric. Okay, so whenever we take derivative with respect to phi, we will get 0. Okay, so this thing is 0. The second one, okay, g theta phi, right? Gamma is phi here. 0, right? Because off diagonal. And the last term is also 0, right? Because we have g beta gamma, which means g theta phi. Again, off diagonal. Okay, 0. So this is nothing but 0. Okay. Li Yong said g theta theta derivative with respect to theta is 0. Right. Okay, right. Yes. Yeah, you're correct. Thank you. Yeah, but the trick is actually the same, right? You can see that the trick is just really try all the indices, okay, to see whether there's some symmetry that we can make use of. If there's some symmetry which makes every term being 0, then we will happily get 0 as a result. But some are tricky, okay? Some are not 0 at all. Like this one here, the theta phi phi component, they are not 0. Even for the alpha equal phi case, things will be the same. Okay? So I think I won't spend time here to do this case. What I can do is very similar to what I just did for the previous question. I will just give you the correct answer for our where's my new page? New page. Sorry, how come my new page isn't coming out? Okay, right, this is the new page. The correct answer would be something like this, cotangent theta. Okay, I mean, for the case of alpha equal phi, okay, you have, of course, you have many other possibility, but they are all 0. Okay, and the non-zero term would be this one. Okay, you're encouraged to try this on your own. Okay, just using the same methods that I just demonstrated. Okay, okay, so let's move to the Riemann tensor. Okay, I'm sorry, it's 5 already. I will try my best to demonstrate this as quick as I can. So now we are asked to compute. Okay, we are asked to compute this term. Okay, but let's consider this version first. Okay, there's a little difference between these two. The theta here is upper index. Okay, because only when I consider theta as upper index can I consider, or can I make use of the formula? Okay, this guy here. Oh, okay. Let me try to write this down with making use of my trick. So theta phi here. Okay, and then what's left is theta phi. So we reverse the order first, phi theta here, and then theta phi here. Okay, this is how I remember the first two terms. And then the second part would be theta phi, right? Theta phi minus theta phi. And then contraction here, sigma or lambda, whatever you name it. And then theta phi. So first, normal order, theta phi, and then reverse order phi theta. So this is how I remember this formula. Okay. So again, if we recall, the non-zero component of the Christoffel symbol is this guy here. Okay. I mean this guy here, as well as this guy here. I hope you are not losing track. Okay. These are the only non-zero components for the Christoffel symbol that we have obtained. Okay. So now we can make use of these two non-zero components to calculate this expression here. Okay, first, can you quickly tell me whether the first term is non-zero or not? The first term here. Okay, maybe let me demonstrate this term first, and then I'll ask you a question regarding the second term. Okay, first, it is a theta phi phi component, right? Do I have a non-zero theta phi phi component? Obviously, yes, right? This guy here. And then now we take the derivative with respect to theta. So what is the result of taking derivative with respect to theta for this term here? Can anybody quickly tell me the answer? This should be a very easy question for you guys. Okay. I just want the answer of this question. What is it? Okay, Leon said minus cosine 2 theta. Okay, I trust you. Trust you. So this would be minus cosine 2 theta. Okay. What about the second term? This one. Can you quickly tell me whether it's 0 or not? Again, the only reference that we have now is just these two start formula. Okay, the only non-zero components of the Christoffel symbols. So is this guy 0 or not? Leon says 0. Yes, correct. Right. Obviously, this is theta phi theta. The one on the left here is not relevant because the top index is phi. So we only need to look at the one here on the right with the top index being theta. But obviously, it is phi phi in the bottom, not phi theta here. So this component of Christoffel symbol is 0, and its derivative will be 0. Okay. Okay, then what about the last two terms? Again, sigma here is contracted. So it really runs over two possibilities, okay, theta and phi. But for the first one here, because we already have theta here on the top, phi at the bottom, obviously this would be 0, right? Because we don't have any Christoffel symbol up here, okay? Which have like theta on the top and then 1 theta at the bottom, but it's non-zero, right? So the first term here is 0. So the whole thing would be 0, okay? Because no matter whether sigma is theta or sigma is phi, right? We don't have a non-zero terms up here to make it non-zero, okay? So the whole thing would be 0. Oh, I should erase this and say that this is equal to 0. What about the last term here? Again, sigma here is run through theta and phi. Either theta or phi. Can sigma be theta? What I mean is, of course, it can be theta, but when sigma is theta, then what would happen to the whole term? When sigma is theta, it means that it is theta phi theta, and then here is theta theta phi. Do we have any term non-zero? Winky said minus cosine square. If theta 0, if phi the non-zero term. Right, okay. I don't know what you mean by the minus cosine square. But Leon said if theta is 0, if phi is non-zero term, that's absolutely correct. When sigma is 0, sorry, when sigma is theta, there is no non-zero terms. Okay, so it's 0. But when sigma is phi, which means I can erase this, and then phi, and phi here. Obviously, this term would be nothing but the minus sine theta cosine theta, right? What about the second term here? Can anyone quickly tell me what is this term? The answer is just right under your nose, actually. Okay, Leon said if phi, then cotangent theta. Very good. Cotangent theta. Okay. Yes, we have this result here. Yes, very good. So now let's just do some tidy up things. So what we have now is let's open. We have minus cosine 2 theta, and then minus 0, and then plus 0, and then minus sine theta cosine theta, then cotangent theta, right? Okay, we hope you have the. Okay, where's my new page? I'm really losing patience on this. And whenever I open a new page, it's really not responding. Okay, anyway, I think this is a very simple math. I won't waste time on getting the page. But now we have this minus cosine 2 theta, and then plus sine theta, plus sine theta, cosine theta, cotangent theta, right? So if you are doing the calculation, we should be able to get like cosine squared theta for the last term, right? And then actually, the cosine 2 theta, oh, okay, it finally comes out. Okay, this is what I have written. So sorry for the delay. So now we have arrived at this line. And if we recall the so-called double angle formula or something like that, we should be able to get something like this. Okay, please correct me if I get this formula incorrect. So this thing is just these things. Okay. He said, yeah, severe lag. Yeah. I think the problem comes from my own device. I really apologize. Yeah, but anyway, the conclusion is the Riemann tensor of, this components, okay, theta phi components is computed to be sine squared theta. But remember, the question actually asks something slightly different. Okay, the theta index is actually a lower index, like this. So what do we do? Well, every time when we want to upper or lower index, we just multiply by a metric. Okay. So now we want this theta to be a lower index. So we write g theta first, and then a contracting index, say lambda, and then the Riemann tensor, something like this. Okay, so this is how we obtain this form here. Okay, I hope you're familiar with this kind of raising and lowering indices. Again, it's contracting, right? Lambda is contracting with itself. And lambda here is supposed to run from either theta or phi, right? But this is metric. If lambda is phi, then that would be off-diagonal components, right? So it would be 0. So only the terms consisting of g theta theta would survive, right? Something like this, right? What about g theta theta here? If we recall g theta theta here, it's nothing but a squared, right? So this will be a squared, and then the r theta upper, and then lower phi theta phi is nothing but sine square theta. Okay. Just that this up here. So the answer would be a squared sine square theta. Okay, so this is the answer. And then of course, although it's not included in this question, we can play around with this expression here by using the symmetric properties, okay, of the Riemann tensor. Like if you interchange the first two indices, you will get something with a minus sign. Okay, or if you interchange the last two indices, you will also get a minus sign. Something like this. Okay. Or if you interchange the whole thing here, the first two indices with the last two indices, you get the same thing. And of course, in this case, it's the same, right? Because theta phi and theta phi are the same. But in general, if you do this interchange, the result will be the same because of the symmetry. And there's another symmetry called the Bianchi's identities, which I won't quote here. If you're interested, you can just look back the notes to play around with the Riemann tensor. Okay, so that's all for the questions of today, and I really apologize for overrunning for like 1.5 hours. And I really appreciate all of your patience here. Okay, do you have any questions at this point? Okay, Winky, you're welcome. Yeah, I really hope that this kind of workshops would be helpful. Yeah, actually, I intended to do this very slowly. Yeah, to re-show the steps, step by steps. Yeah, because I also understand that sometimes it is quite not trivial when you do all the calculations, especially when it's your first time to see all these kind of tensors, indices also. Okay, you're all very welcome. And Kohe say, okay, it's nice to always recap on previous techniques. Yeah, actually, even for myself, I'm also, how to say, kind of doing revision for myself when I actually do all these calculations. Even for the tricks that I said, I also took some time to remember it, to record it, which is something that I remember like many years ago. Yeah, so you're absolutely right. It's nice to always recap. Okay, what about other students? Do you have any other questions? If no, then okay. Thank you very much again for coming. I'm super sorry for the very overrun session. I hope you have a very fruitful reading week ahead. And yeah, that's all for today. Okay, so maybe see you next time. Bye. Thank you.